Thank you very much for the introduction and for the invitation to speak here today. As already stated, my title is a new Northcott property for the Faltings type. I'm going to start with an introduction and a motivation for the problem which I considered, and then go into the statement of the theorem, an outline and strategy of the proof, and then go into more details, getting through as much as possible in the next 55 minutes. All right, so first, intro. In this first part, we're going to fix K. Everything is going to be global in this first part. So K is going to be fixed to be a number field, and OK inside of K is, as usual, its corresponding ring of integers. A over K is going to denote an abelian variety of dimension G. And we're going to put the assumption throughout this talk that every single abelian variety has semistable reduction everywhere. So I won't mention that again, but just keep that in mind, that whenever I talk about abelian varieties, they will have semistable reduction. Curly A over OK denotes the corresponding neuron model. And we recall from the theory of neuron models that there's an extension of the identity section on our abelian variety to the neuron model, which gives a map from spec of OK into the neuron model. Omega sub A is going to denote the Hodge bundle, which is the pullback under this extension of the identity section of the Gth exterior power of the Kähler differentials, of the sheaf of Kähler differentials on our neuron model. And finally, because we're going to be in the setting of our Artin theory, we're going to equip our Hodge bundle together with a collection of Hermitian metrics and make it into a Hermitian line bundle. So whenever I'm talking about Hermitian line bundles, I'm going to denote it as a line bundle together with a bar. And that just means that it's the pair of the line bundle together with a collection of Hermitian metrics, which corresponds to all the embeddings of our number field into the complex numbers. In this case, we have a very explicit definition of what these Hermitian metrics are, which is the following. The square is going to be the normalized integral of our abelian variety given a differential structure under the embedding sigma, where here alpha, I'm going to write it over here, where alpha is going to be a global section of the sheaf of differentials on our differential abelian variety. And that is identified with the Hodge bundle under the extension given by the embedding sigma. Our main player of the game today is the Faltings height, which is defined as the following. It's an invariant that is attached to our abelian variety, and it's given as the Artin degree of our Hermitian line bundle, of our Hermitian Hodge bundle. This can be written formulaically, and also an equivalent definition, which was actually Faltings' original definition, as the normalized difference between two volumes. The first is the arithmetic volume, and the second is the Archimedean volume, which corresponds to every single embedding of K into the complex numbers. And here, in this formula, we have that alpha is just a global section of our Hodge bundle, and it's independent of this choice by the product formula. So taking this latter as a definition is perfectly fine, and it's actually going to be the definition that we will want. So the reason that Faltings introduced this Faltings height is to be able to answer the Mordell and the Shafarevich conjectures, which are reduced to the following finiteness statement, which now, in the current theory of heights, we call it to be a Northcott property. So Faltings' Northcott property is the following. It states that given two constants, c and d, and some integer that is greater than 0, then the set of abelian varieties, A over a number field k, which satisfy the conditions that the dimension of A is fixed to be G, the degree of the field of definition of K over Q is bounded by D, and the Faltings height of these abelian varieties is bounded by C, that this set is going to be finite. And the way that Faltings proves this is by looking at the Siegel moduli space of abelian varieties, constructing an embedding into a projective space, and doing a comparison of heights. So in today's theory of heights, this is not a very intrinsic Northcott property to the Faltings height, which motivates just an intrinsic question whether there is a more intrinsic way how to find a Northcott property for the Faltings height. So a good place to start is whether there's a way how to find a CM version of a Northcott property. The CM abelian varieties behave particularly well. So in order to explain what I mean by a CM version of a Northcott property, I'm going to define for you what I mean by a CM abelian variety. For this talk, I'm just going to restrict everything to simple abelian varieties just because it's notationally and technically simpler. But all of this theory holds for a more general case of CM abelian varieties. So we say that a simple abelian variety, A, a priori defined over the complex numbers of dimension G, has Cm by the pair E and phi if it satisfies the following two conditions. Well, first I should say that E over here is a Cm field, and phi over here is what is going to be called a Cm type. A Cm field is a number field which essentially is defined as having a unique complex conjugation. And a Cm type is going to be defined as something more intrinsic to the geometric structure of an abelian variety. So the first condition that it has to satisfy is that this Cm field has to embed into the rational endomorphisms of our abelian variety, which is just our endomorphism ring of our abelian variety tensored up to Q. We also impose a condition that it's going to have Cm of full rank, so that the degree of E over Q is going to be equal to 2G. This condition actually makes this to become an isomorphism instead of just an embedding. The second condition that we impose is that E has to act on Lie of A along phi. So in particular, it's going to be, so what this means is that this phi is going to be a subset of G embeddings of E into the complex numbers. And we impose the condition that phi has to be disjoint from the elements of phi composed with complex conjugation. And of course, because it's half the embeddings, that this is going to have to equal to the set of all of the embeddings of E into the complex numbers. So the main advantage that we have in working with Cm abelian varieties versus arbitrary abelian varieties is that there's a lot of arithmetic information that is carried and that has been known due to the work of Shimura and Taniyama. In particular, Shimura and Taniyama have shown, or what is at least now called attributed to Shimura and Taniyama, are the following two statements about Cm abelian varieties. The first is that every Cm abelian variety descends to a number field, K. And the second part is that there exists a finite extension, K prime, of K, such that if you base change the descended abelian variety to K prime, then this abelian variety has good reduction everywhere, which is much stronger than just having semi-stable reduction everywhere. In particular, if it has good reduction everywhere, then its neural model is itself going to be an abelian scheme. So, keeping this in mind, the theorem that I showed, the new Northcott property, well, it comes in two parts. So again, we fix some constant and some integer that is greater than 0. The first part is that if you fix some abelian variety a priori over the complex numbers, which has Cm, then the set of all abelian varieties inside of the C or the Q bar isogeny class, but let's just say C isogeny class of A naught of bounded Faltings height, this is going to be finite. And the second part, B, is that if we assume the Colmez conjecture and the Artin conjecture, the Artin conjecture being that Artin L functions are going to be entire, then we have that the set of Cm abelian varieties A over C such that their dimension is fixed and their Faltings height is bounded, that this set over here is going to be finite. And there are several remarks that I should make about this. Very first, and probably the most important, is that this theorem does not imply Faltingses, nor does Faltingses imply this theorem. In particular, the abelian varieties that you find in this set are going to have varying fields of definition, which you can already start seeing in the case of elliptic curves, because when you have Cm elliptic curves, then there's a one-to-one correspondence between fields of definition and the ring class fields that you get from local class field theory. So you are going to have some growths of fields that you have to take into account in proving this Northcott property. The methods also are completely different in this theorem, and it's something which is much more intrinsic, does not even use the moduli space to be able to prove such a Northcott property. I should also say a few more remarks about this. So first, B at this point is unconditional for elliptic curves and for abelian surfaces. And then moreover, the Colmez conjecture is true for Cm fields, which are Galois. In many cases, up to G equals 3, and some other cases which are, I guess, now in progress. This is due to Colmez, Obis, Young, some work by some of his students, and some things which are in progress, so plus epsilon over there. So I just want to make one more remark about part B. Part B is deduced from part A with the assumption of these two conjectures. And the main idea in deducing part B from part A is to use the Colmez conjecture to give a new expression for the Faltings height for very particular Cm abelian varieties within isogeny classes, and then finding a bound below using the Artin conjecture in terms of the logarithm of the discriminant of the Cm field. And that allows you to count. I want to focus more on part A in this talk and the strategy of the proof, and to go much more into detail about that. I think I can do this simultaneously. Nope? No, I can't. I was hoping that I could. All right, so while that's going up, I'm going to start with revealing this, which I had hidden, the Faltings isogeny lemma, since that is going to be our main computational tool in order to be able to prove part A. So the Faltings isogeny lemma is something which is a lemma. It's not difficult to deduce from the second formula of the Faltings height. And it basically states that if I have an isogeny between two abelian varieties, then I can compute what the difference in their Faltings height is going to be. And it's not going to be, and the Faltings height is not an isogeny invariant, and that is very important. In particular, it is not supposed to be an isogeny invariant. And you can find that the Faltings height, the error is going to change. Well, there are two error terms over here which compete against each other. So I point out also over here in the statement of the Faltings isogeny lemma that this G in the kernel is a finite flat group scheme over OK. This makes the computation of the relative differential to be easier. And this is going to be true in our case because we have good reduction everywhere for A1 and A2. So there are two terms which come out. This comes from the difference between the two Archimedean terms, so the difference between in the volume form for the definition of the Faltings height, and this is the difference between the two arithmetic terms. And so we want to, the game that we play is we want to play one term off against the other. But there are some reduction steps that we can do to make this game a lot easier. So first, we reduce everything, I should say strategy of A. So the first step is to reduce everything to p isogeny classes. And this means that this will allow us to analyze, instead of exact sequences on the full abelian variety, we analyze exact sequences of this form on instead the p-divisible groups. Where this G, as long as it's a p isogeny, is going to be the same G that appears in that isogeny exact sequence. Then, within each of these p isogeny classes, we find an element that is minimal. So we distinguish a minimal element inside of each of these p isogeny classes, which actually turns out to be a global minimal element. So we distinguish an A0 with minimal Faltings height inside of the classes. And I'll just give a spoiler that this is going to be the CM abelian variety with CM by the maximal order. Then we classify all the subgroups that are contained inside of the p to the n torsion of our CM abelian variety. And this classification is via Farg's Harder-Narasimhan theory for finite flat group schemes of p power order. And this is a more refined theory to the theory of the Newton polygon, and is in particular very amenable to be able to relate back to and analyze the changes in Faltings heights. And finally, what we do is we compute the Harder-Narasimhan slopes in this theory, which are going to then relate back to the computation of the Faltings height. And this is done via Kissen's theory of Kissen modules. And the Harder-Narasimhan slopes that we compute are going to be for very, very specific isogenies, which I will get to when we get to the part where we classify these finite flat group schemes via the Harder-Narasimhan theory. All right. So at this point, I'm going to switch gears entirely to get into the details. And the first thing that we're going to review is the theory of Kissen modules. So this is a local theory, which means that now we're going to switch notation. We're going to let little k to be a perfect field of characteristic p. The example to keep in mind is a finite field like Fp. W is going to be the ring of bit vectors that correspond to this little field k for Fp, that is just Zp. K0 is going to be the fraction field of W, and so the fraction field of Zp is Qp, and K over K0 is going to be a finite, totally ramified extension of degree E. And in particular, from the structure theory of local fields, this means that this extension is going to be given by an Eisenstein polynomial. And the structure of an Eisenstein polynomial takes the form u to the e plus, well, let me just write this out, where for all I, well, p has to divide all the coefficients, aside from the first coefficient, for all I, and p squared cannot divide a naught. So using this setup, we can define the relevant objects from p-adic Hodge theory, which will be useful for our computations. And most generally, with a minimal amount of decorative adjectives, we can say that a Kissen module M is, there is one more thing which I need to define. Let me actually just pull this back down and then I'll just push it back up. So there's one more ring, which is very important. This is the ring sigma, which is W adjoining an indeterminate U. And actually, there's more that I should say about this. This ring sigma over here is a very specially constructed ring by Kissen in his whole theory of Kissen modules. And we don't just want to consider the ring itself, we want to consider it together with the Frobenius structure. So there's a Frobenius structure on our little field K because it's a perfect field. This lifts to a Frobenius structure on the ring of Witt vectors. And over here then, we have the same Frobenius structure on this ring W, but then we want to extend it to the indeterminant, and so we take it just by mapping U to the P. All right. So that's supposed to be a math frac S. I might sometimes refer to it as a sigma or a frac S, but it's supposed to be a math frac S. So a Kissen module M is going to be a frac S module together with an endomorphism phi M, which is called the Frobenius, which satisfies a Stuka condition, which states that if I pull back the coefficients of my module under phi, so I look at this, and then I map using the Frobenius to M, then I do not get an isomorphism on the nose, but I do when I invert a chosen Eisenstein polynomial. So this is how the data of the ramified field comes into the data of a Kissen module. That should be an isomorphism. There are some subcategories of Kissen modules which are very useful for us. These have some more adjectives over here. So the first is BT phi 1, which is going to be those Kissen modules which are also free as sigma modules. And there's also mod phi 1 over sigma, which is going to be those which have a two-term resolution by elements of BT phi 1. And both of these also have the additional condition that there exists a unique endomorphism called the Verschiebung, which satisfies that the Frobenius composed with Verschiebung is equal to multiplication by the Eisenstein polynomial. So at this point, for those who are more familiar with classical Diogenes theory, might recognize some of these conditions to be very reminiscent of Diogenes modules. And there is actually a very strong connection between these Kissin modules and Diogenes modules. And the main theorem that was shown by Kissin and extended by Tong Liu in the case that the prime is equal to 2 is the following, that there exists a contravariant equivalence between the category of p-divisible groups over OK and this category BT phi 1 and this category of finite flat group schemes of p power order and the category mod phi 1 over sigma. And this is stronger than the classification by Diogenes theory because Diogenes theory classifies everything up to isogeny. This classifies everything up to isomorphism. There are some facts about this equivalence. Well, first, I'm just going to say that the functor in this direction is called M. The functor in this direction is called G. So there are some important facts about this equivalence. There's one which I single out, which is that if we have a finite flat group scheme of p power order, then we have a bijection between finite flat subgroup schemes and saturated submodules of the corresponding finite flat group scheme, where here saturated means that if I have a module, then it inherits the lattice structure from the larger module that it's contained inside of. And this correspondence is done in the following way, or it's obtained in the following way. If I have some finite flat subgroup scheme over here, then, well, under this map M, it's going to map to the quotient of M of G by this saturated submodule, since this equivalence is contravariant. And this coincides with M of H. All right, so if we want to understand then subgroup schemes of a given group scheme, it's sufficient to understand saturated submodules of a larger Kissin module. There is one more fact about these Kissin modules, which I want to state, which is a key proposition for why these are the right tools in some sense, or why these are the right tools to look at to be able to do the computations, to be able to prove this theorem. So the key proposition is that these are very computable, so that if K, our perfect field, is just a finite field, say on Q elements, and G is a finite flat group scheme of p power order, and let's just say that it's killed by P, then we can compute this module, which appears, we can compute this module, which appears inside of Faltings' isogeny lemma, or the size of this module, which is sufficient for us, to be Q to the u-adic order of the determinant of our Frobenius on our Kissen module. So this determinant is going to be well defined up to some unit inside of W, but since we're only looking at the p-adic order, that is sufficient for us. All right, so now we have a problem that we're used to this abstract set of tools, which we have a proposition that tells us that these abstract set of tools can make this problem very computational as long as we can compute what the Frobeniuses of these elements. So now we actually want to be able to compute what the Frobenius of these elements are, of these objects are. So,
what is K on the left-hand side?
This little k?
No, the OK.
This k is that k, the ramified k.
Okay.
Yeah. Okay. So the next step is to be able to compute the Frobeniuses. So we compute what I call OEP VP linear CM Kissen modules. We're going to let now EP VP be a localization at P of a global CM pair. Which we call a p-adic CM pair, but terminology is not so relevant. For simplicity, we're going to just make the assumption, this is just for this talk, that this is going to be a field. All right. So in this local theory, just like in the global theory, we have the notion of a reflex norm. And it's constructed in exactly the analogous way. So, right, so we assume that EP is a field for this, for simplicity. And we also assume for this that K is large enough. There's a precise way how to say what large enough is. Then there's this map, the p-adic reflex norm, which takes multiplicative elements of K and it maps it down to multiplicative elements of E, factoring through an intermediate module. And this map explicitly can be defined by taking an E-linear determinant of this element X acting on some k-tensored E module, V phi k, where V phi k can be any module that satisfies that if you tensor it up to QP bar, then it's going to decompose along, I think that's supposed to be over, and then it's going to decompose into a direct sum of copies of QP bar corresponding to each of the elements inside of your CM type. And this over here is going to be a E-tensored K module. All right. There's also a relative version of this reflex norm. So if we have L inside of K, a finite index, then we can define this relative version of this reflex norm as the following map, where again, we're going to take an element, multiplicative element of K, factor it through K tensored E, but instead of mapping it all the way down to E, we map it down to L tensored E, and this decomposes into a product of CM fields. Well, p-adic CM fields. And the map can be defined by taking an element and then mapping it to the product of the EI linear determinants of X restricted to each of these modules corresponding to the EI. This relative reflex norm can then be tensored up to give a multiplicative map on such power series rings. And in doing so, we're allowed to define for all multiplicative elements inside of K a characteristic polynomial with respect to this relative reflex norm sorry. So all of these E's are supposed to have a P underneath it. Everything is localized. So up there too, they're supposed to have a P and the subscript. When I switch words, I'll quickly change it. So this is the relative reflex norm of just U minus X. All right, so now we have a definition that an OEP, VP, linear CM Kissen module is a rank 1 projective frac S tensored OE module such that the Frobenius acting on E is, well, up to some unit, multiplication by the relative reflex norm characteristic polynomial constructed on the opposite CM type on our uniformizing element of K with respect to this K naught and multiply that with E. And then proposition is that if we let M be an OEP VP linear Kissen module, then M is going to be the Kissen module that is attached to the p-divisible group, or that comes from a CM abelian variety by OE phi. Right, and over here, all of these should have p's, because everything is local. There we go. So this point, it still seems very abstract, but actually these are very computable. And we'll give two examples of how these look like. The first is that if P is inert in OE, then the set of embeddings of EP into QP bar, first of all, is a Z mod 2G Z torsor, which tells us a lot about the structure of the Frobenius just in and of itself. Our Kissen module is going to decompose onto 2G generators, where we can choose these basis elements to respect this Z mod 2G Z torsor structure. So they map to EI plus 1, but those that correspond to elements inside of the CM type get multiplied by the Eisenstein polynomial, and otherwise there's nothing. The second example is we're going to take G equals to 1, so the case of an elliptic curve, and P is ramified in OE. Then in this case, we're going to have our Kissen module to decompose into two parts, ME1 plus, sigma E1 and sigma E2. And here, Vn modulo P has a particularly nice form that it's going to be upper triangular. The elements along the diagonal are going to be u to the e divided by 2g. So in this case, it's e over 2. And the elements along each of the superdiagonals, the elements along the diagonals should be the same, but the degrees are going to be decreasing. So in this particular case, we can compute it very explicitly using Lubin-Tate theory under some representation to look something like this. And so in the remaining time that I have left, I want to go into classifying these modules. So at this point, what we have is the structure of the p-divisible group that corresponds to the full p-divisible group, from which we can extract what the structure is going to be for the p-torsion, for those that have maximal order structure. And now we want to be able to compute submodules, saturated submodules. The Frobenius is the saturated submodules inside. But we cannot just compute them ad hocly. We want to be able to classify them first and know which ones exactly to compute. So, classifying subgroups and computations. So I'm going to just fix now M0 to be the Kissen module that is going to correspond to the p to the n portion, where A0 over here has Cm by the maximal order. And we're going to let now G to be finite flat group scheme of p power order. And we define a quantity which is called the Harder-Narasimhan slope of the Kissen module that is attached to G, which, well, up to a normalization factor, is going to be B over A, where B and A are these quantities that appear in exactly the Faltings height isogeny formula. So this is up to a normalization of the slopes so that you know exactly which range you want this to be in between. So up to normalization so that the slopes are going to range between 0 and 1. But the point is that these Harder-Narasimhan slopes are going to quantify what the ratio between these two terms are. So then just using the abstraction of Harder-Narasimhan theory, we're able to discover a lot of things, just how these two terms play off against each other. In particular, Artin theory gives us the notion of a semistable element. And the semistable element is classified or defined by saying that for every single subobject, so every single finite flat subgroup scheme inside of G, the slope of H is going to be less than or equal to the slope of G. And this is really good for us because this already tells us that as long as we can understand semistable elements, we already have that in some sense, we already have that this Archimedean term is going to dominate this arithmetic term. So a proposition is that M0 decomposes as the direct sum of semistable elements. In this Artin theory. And this is important exactly for what I just said. I should also say that this decomposition is something that is actually very easy to understand and to compute because this decomposition happens to be exactly along the prime splitting inside of the CM field. Right, so once you split your primes, then each of the corresponding p-divisible groups are going to have, when you split a prime, then the p-divisible group is going to split into a product of p-divisible groups, and each of those p-divisible groups is going to be semistable. We're going to say that a saturated submodule inside of M0 is level changing if it's exactly the type of subgroups that we want to classify. So if it corresponds to an isogeny exact sequence of the form 0 to M of G prime to M0 to M0 mod n, where here this G prime is going to have p-adic Cm by an order that is not maximal. Then just using the abstraction of Artin theory and some of the symmetry that you have from CM theory, you can show that if you have a saturated submodule of M0, then this is level, this is level changing if and only if the slope of n under this decomposition, so each of the decomposed pieces, is going to be strictly less than the slope of mj. And this tells us that as long as we can, in effect, compute semilinear eigenvalues and then compute all the saturated submodules, then we know exactly which ones are going to correspond to orders. And that specific computation that we do for these slopes gives exactly what the change is going to be over here. So in the last, I guess, a little bit more than 5 minutes, just want to state one computation in the easiest case to show what are the types of bounds that can be obtained. So this is the easiest case. So if we let A over K to have Cm, and I guess this proposition is going to be stated in the global form on abelian varieties. So if we let A over K have Cm by OE phi, and we assume that P is inert in OE, and we let a sub p to the r over k have Cm by O phi, where here O is assumed to be a non-maximal order with index equal to p to the r, then if we choose the minimal isogeny between the corresponding neuron models, which would mean that the size of the subgroup is going to have to be, in the kernel is going to be p to the r. H has to be p to the n torsion for some n that is going to be less than or equal to r. And finally, we just quantify that the size of the p torsion is p to the k. Then we can obtain the following type of bound for this quantity. It's going to be less than or equal to 1 over p plus 1. And two other terms we multiply by log p. Where over here, if we start looking at these terms, we see that this first term allows us to vary primes. This last term over here allows us to vary prime powers. There is this artifact term, which would be interesting to figure out what you can do with that. But the point is that if we look at this, and then we look back at this formula over here, the comparison that we have to make with this to that is against r over 2 log p. And so we get, and so that allows us to be able to count and to be able to get that, get the right discretization and to get that the Faltings height within isogeny classes as we change these orders. That there is going to be, we get the count that there is going to be finitely many. So the last thing that I do want to say about this is that equality is possible to obtain in some cases, and that this is a general bound just by doing some general reductions, finding that some CM types, basically some CM types are better than others. But in every single case where the prime splitting and the CM type is explicitly known, it is possible using these techniques to compute exactly what this quantity is in the CM case. For every single case, not just for those which are inert or just for those that are ramified, but very explicit and direct information has to be given exactly on the CM type and the prime splitting. And these computations are not easy, so I do everything in an appendix of my paper for abelian surfaces with cyclic Gauss, whose CM field has a cyclic Gauss structure. And just the ramification takes 9 pages of computation. So it's not easy, but it's possible to do very explicitly for every single case. All right, so I will end here. Thank you very much once again for the invitation, and thank you for being such an amazing audience.
Okay, thank you. So we are perfectly on time, so we have time for questions.
Can you count?
You mean to get an effective number of these? No, because one of the implicit things in all of this is that I assume that over every single, so like take the case of elliptic curves, right? Over every single ring class field, you know that there are only going to be finitely many isomorphism classes, but you cannot actually count how many there are, even in the case of elliptic curves. Like, you know which fields have class number 1. You don't know over the ring class fields how many there are going to be of isomorphism classes, except that there are finite. And this is necessary.
Not quite.
I
mean, you seem to be arguing why it's hard to actually compute the exact number, but I'm just asking for upper bounds.
For the number of abelian varieties
that
I have.
In case A, for instance, in case A. So in the part A of your theorem.
Yes. Right. Okay.
So even to give the upper
Right,
bound.
Is there an upper bound on class numbers?
I mean, probably not effective, right?
Right. So then, no.
No, but I mean, effectivity is a different thing. It's just the growth that I'm asking. We can chat about this later.
We should chat about this later.
Other questions? Okay, so if not, we can thank the speaker again.